Hello everyone, my name is Yulia Kotsuruba. I'm going to talk about benchmarking pedestrian action prediction. This work was done with my colleague Amir Rasuli and supervised by Professor John Tsotsos. Predicting pedestrian crossing action is important for intelligent driving applications. However, despite recent proliferation of models that solve this problem, there are no benchmarks based on publicly available data. As a result, existing models use different problem definitions, evaluation protocols, and datasets, which makes it difficult to compare different approaches. To this end, we propose a benchmark with the following task definition and data. Crossing action prediction task is a binary classification problem. We would like to predict whether the pedestrian will cross at time t, given the observation of length m that ends sometime before the event. For the evaluation, we use two publicly available datasets, pedestrian intention estimation or PI, and joint attention for autonomous driving, JAD. We will use train, validation, and test data splits as provided by the dataset annotations. For the evaluation, we use approximately half a second of observation and sample pedestrian tracks at 1 to 2 seconds prior to the event. The event starts when the pedestrian begins to cross the road. If the pedestrian does not cross, we use the last frame where the pedestrian was visible as the event frame. We evaluated a number of baseline and state-of-the-art models for action prediction and recognition. These were divided into 4 groups. Static models predict action based on a single frame. RNN-based models use both visual and ego-vehicle data. 3D convolutional models form spatio-temporal representations from stack of frames. And two-stream models process image and optical flow in parallel. All of these models were trained and evaluated on PI and JAD. We also performed hyperparameter search to get the optimal performance for each algorithm. We considered 2 subsets of JAD. JAD all, that includes all annotated pedestrians, and JAD behavioral, which includes only pedestrians with behavioral labels. Here's a table with the overall results, which indicate that RNN-based and 3D convolutional models perform the best on all datasets. As part of the evaluation, we investigated model agreement. We divided samples into 3 groups, easy, medium, and difficult, depending on whether they were correctly classified by all, some, or none of the models, respectively. Overall, there was no correlation between sample difficulty and properties labeled in the dataset, which include time to event, occlusion, scale, and semantic properties. However, there are other unlabeled factors or a combination of factors that could correlate with difficulty. We also considered effects of time to event, occlusion, and scale on performance. As expected, it is easier to predict action closer to the event. As illustrated, performance is highest at 30 frames TTE and then gradually decreases for predictions farther from the event. Since only 1 or 2% of the data is occluded, performance on the occluded samples fluctuates significantly. Size and distribution of the bounding boxes in the training set matter as well. Note that majority of the bounding boxes are between 80 and 50 pixels in size. This is where the performance is stable. However, it starts to fluctuate outside that range. Given the results of the benchmark, we proposed a new pedestrian crossing prediction model with attention. It combines RNN and 3D convolutional streams in a hybrid framework. RNN streams independently process bounding boxes and poses of the pedestrians and ego-vehicle speed. Temporal attention is then applied to assign weights to temporal representations. A separate 3D convolutional stream processes visual context, which is an image of the scene cropped around the pedestrian. Finally, we apply the same attention block as before, but this time it plays a role of modality attention and assigns importance to representations from different branches. A fully connected layer predicts the crossing action. Here are the results of the proposed model. It achieves state-of-the-art performance on both PI and JAD all. JAD behavioral is much smaller and tends to overfit. In an ablation study, we show that attention mechanism improves the results. We also show that using the entire scene as the visual feature works better than pedestrian appearance or local context. To conclude, we presented a benchmark for pedestrian action prediction, which is based on 2 publicly available datasets, PI and JAD, and the newly proposed evaluation protocol. We analyzed different architectures and found that their performance does not correlate with sample difficulty. We also proposed a new hybrid model, PCPA, that achieves state-of-the-art performance on both datasets. The code for the benchmark, baselines, and the proposed model is publicly available following the link below. Thank you very much for your attention.